Hi one and all, this is Steven from Aero B section. Today I am taking physics tech talk. My topic is aerodynamics interference in aircraft directional control. This work investigates the aerodynamic interference among airplane components caused by rudder deflection for a typical turboprop aircraft geometry through the computational fluid dynamics technique. At no side slip, an airplane is in symmetric flight. At no side slip, an airplane is in symmetric flight conditions. The rudder deflection creates a local side slip angled close to the vertical tail plane, and this effect is increased by fuselage and horizontal tail. Typical symmetrical methods such as United States Air Force stability and control data pendulum, nothing but USAF, DAT, COM, do not take into account for these effects. Proposing the same corrective parameters both for pure side slip and rudder deflection conditions. Numerical analysis executed on several aircraft configurations with different wing and horizontal tailplane positions show that the interference factors are smaller than those predicted by the USAF DATCOM procedure, providing guidelines for a more accurate aircraft directional control analysis and hence rudder preliminary design. Let's see the modern problems of aircraft aerodynamics. First we have go to in background. The latest successes of aviation science and technology in fuel efficiency increase could be observed in figure 1. There is a significant reduction of fuel consumption for passenger per kilometer, but not only has the fuel consumption indicated aviation science development, the flight safety and ecological impact, degrees of noise and environment pollution level of aviation transport became the prime task of development. In this, we have checked the flight. Mostly first we check flight safety and ecological impact like decreasing the noise and environment pollution. In 2014, there was document prepared by representatives of Russia, leading scientific organizations like TSAGI, CIAM, PIAM, GOSNIS, etc., named by Foresight of Aviation, Science and Technology Development, which defines the long-term free cost of scientific and technological development of Russian Federation in area of aviation industry. Each document specifies the ambitious task indicators of creating a backlog in the area of civil aviation development, which could not be achieved without reconsideration of exciting technologies of aviation science. The Brigade Flight Range Formula LKM CE in G1 and Go allows to define the key aerodynamic parameters which needs to be improved. First of all, it is an increase of cruise lift to drag level K, capital K, cruise Mach number capital M, and decrease of specific fuel consumption and minimization of structural weight G1 and GO masses of aircraft at the beginning and at the end of flight. Observe the table. It is showing change of root aircraft fuel efficiency with time. Let's go into it. In 1965, it is gone to 62, and let's check where lambda the effective wing accept ratio, CF skin friction coefficient, sweated the wetted surface area of aircraft divided by wing area. Thus, there are another three different directions of flying vehicle economical characteristics. Improvement related to aerodynamics, aspect ratio increase, friction drag reduction and aircraft relative wetted area decrease. The main components of full cruise drag of modern aircraft are frictional drag, drag due to lift, and wave drag. The impact of the first two in transonic speeds region reaches up to 50 and 40% of full drag correspondingly. This shows that friction drag reduction is a major source of aircraft lift to drag increase. It should be noticed that lift to drag increase is not only about drag reduction but also about increase of lifting capabilities by shape, improvement and search for newer layout solutions. In the near future, the development of aerodynamics layout of router aircraft will be carried out in frames of classical layout basing on progress in area of aerodynamics of high-speed wings, new materials, electronic and electromechanical devices, and super high bypass ratio engines. The article also examines peculiarities of aircrafts of integral layouts, flying wing, elliptic fuselage, and aircraft with distributed power plant and power plant integrated into the wings. The main directions of aircraft classical layout development. It should be admitted that aerodynamic potential of modern supercritical wings is on the edge of limit. That's why it is needed to investigate and implement some new prospective technologies in order to move forward. Among them, the following should be outlined. Adaptive wings of for transonic speeds, new types of wingtips, organization of laminar flow around empennage, engine nacelles, and ladder around wings, NLF, HLFC. Reduction of turbulent friction drag improves types of efficient high lift devices, active and passive flow control systems, mini and macro devices, synthetic jets, actuators, etc. Active thrust vectoring control, transition to layouts with moderate stability, margin and slightly unstable layouts. Most frequently, the higher speeds possibilities of supercritical wings are traded for increase of relative thickness of the wing in order to reduce structural weight for to increase accept ratio, which as is well known leads to reduction of drag due to lift. It is a picture of layout of aircraft with wing brasses. Let's observe in it. The important reserve for aerodynamic layouts. Lift to drag level increase in the optimal positioning of engine nacelles, which is quite actual due to tendency of increase of bypass ratio and sizes of prospective engines. It should be noticed that high bypass ratio engines have smaller fuel consumption and lower noise levels but have a negative effect on flow around airframe, including takeoff and landing paces due to limitations on span and extension distance of root section of slat. Besides that, large side engine nacelles located under the wing require longer undercarriage struts that leads to structural weight growth. Application of optimization procedures allows to significantly decrease negative interference of nacelles. The loss of maximal lift while using insufficiently effective high lift devices could be compensated, for example, by application of jet blowing in wing pylon connection area. Experiments on investigation of efficiency of this conception have already started at TSAGI on large scale spare flying wing aircraft concept. It tells us the integral layout flying wing nothing but FW, or it is also called as blended wing body nothing but BWB is considered to be the most aerodynamically perfect layout for long range aircraft. Flying wing concept is targeted on full elimination of fuselage as a main part of drag. Besides that, for classical flying wing, tail empennage is also absent. Theoretically, the lift to drag ratio for flying wing could be 40% higher than that of classical aircraft for the same wing aspect ratio. Besides that, the aircraft empty weight for flying wing layout should be less due to possibility of more uniform distribution of payload inside wing. However, more complex problems of balancing and controllability of flying wing inevitably and potentially passenger aircrafts. A flying wing layout possesses three advantages: higher lift to drag ratio due to smaller relative wetted area, favorable distribution of mass, load along wingspan, and relatively small ground. Noise level for configurations with engines located above airplane. However, taking a closer look, these advantages do not look that obvious. The modern problems of civil supersonic transport aircraft. Let's check in this. What is the modern problems in transport aircrafts? The main factor told the development of civil supersonic transport in Russia and abroad is the absence of conventional rules and requirements on sonic boom. A transition from overpressure terminology to loudness terminology allows to evaluate the level of sonic boom more advocate and uniquely and to formulate the CSST layout with low sonic boom level. At the time, the process of formulating rules on sonic boom came into active stage. The specialists of TSAGI and GOS, NIIGA and FRI are involved into the process, including the frames of RUMBLE Rumble. It's a European project. Main talks of this project is to formulate of proposals for positive rules on sonic boom, regulating acceptable levels on sonic boom thresholds, levels on sonic boom threshold levels, measurements, metrics, and methods of determining the compliance of CSST to these rules. The analysis of the metrics and threshold levels discussed by World Scientific Society 11 to 13 allowed Russian specialists to formulate preliminary requirements on sonic boom for prospective SST. The preliminary list of proposals on requirements for metrics and threshold levels is already developed. Thank you. Thanks for all.